Yeah? Ha. Saranama. Ha? Ha. सर कुठं आहे? कुठं? होय? बरं.
Good morning all. On behalf of organizer, Department of Chemical Engineering, Padma Bhushan Vasantrao Dada Patil, Institute of Technology, Budgaon, Sangli, I, Dr. Sangram S. Patil, welcome you all for the AICT Training and Learning Atal Academy sponsored faculty development program on computer science and biology with topic applications of computational techniques in chemical engineering and biotechnology. Now I request Professor Unmesh Padil sir, Head Chemical Engineering Department, IIT Budgaon, to introduce the workshop program. Sir. Sir. HOD sir, please switch on your microphone.
Good morning, one and all. Respected Gaurav sir and his Atal team, respected Dr. Sanjay Mahajani, Honorable Sri Vishal Dada Patil, Chairman Dr. Vasantrao Dada Patil, Shetkari Shikshan Mandal, Honorable Sri Amit Dada Patil, Trustee, Honorable Sri Adinath Magdum, Secretary of Dr. Vasantrao Dada Patil, Shetkari Shikshan Mandal, Honorable Sri Rajput sir, Chairman, Governing Council, PVPIT, Dr. Ghevde sir, Principal, Padma Bhushan Vasantrao Dada Patil Institute of Technology, Budgaon, Sangli, and all the participants. It gives me an immense pleasure to welcome you all in this 5 days AICT sponsored FDP under AICT Training and Learning Scheme in Computer Science and Biology as applications of computational techniques in chemical engineering and biology. As per the need of the day, we all academicians need to update ourselves for the new technology and new softwares in chemical and biotechnology field. A modern chemical plant consists of interconnected units such as heat exchangers, reactors, distillation columns, mixers, etc. with high degree of integration to achieve energy efficiency. Design and operation of such complex plants is a challenging problem. Mathematical modeling and simulation is a cost-effective method of designing of or understanding behavior of these chemical plants. Mathematical modeling cannot substitute experimentation. However, it can be effectively used to plan the experiments or create scenarios under different operating conditions. Thus, the best approach to solve most chemical engineering problems involves combination of mathematical modeling and carefully planned experiments. Today, professionals in chemical engineering and biotechnology field have to deal with complex problems which cannot be solved easily. Most of the processes are characterized by a set of nonlinear equations which are difficult to solve. Modern computing tools are available to solve problems related to design, optimization, and control of processes to get better productivity with minimum energy costs and prevent wastage of the valuable materials. Computational techniques can help to develop efficient process and reduce production costs of industries. In this context, the FDP aims at providing insight into applications of computations methods to analyze and solve problems related to chemical engineering and biotechnology for the better yield and productivity. Objectives of this FDP are to refresh the basic concepts of numerical methods and computing in engineering applications, to demonstrate use of computing applications for solving chemical engineering problems, to explore opportunities in the field of computational biology and bioinformatics. For this FDP, we are fortunate to have experts from academics, research, and industries as well. Today, we have golden opportunity to listen Dr. Sanjay Mahajani from IIT Bombay, followed by Dr. Yogesh Mahajan from Dr. Babasaheb Ambedkar Technological University, Lonere, Dr. Nilesh Madi from NCL Pune, and then tomorrow onwards, we will be having Dr. S.S. Bhagwat from ICT Mumbai, Dr. Sapkar from Amaravati University, Mr. Sunil Patil, who is Principal Consultant in Aspen Tech, and all other eminent personalities. I hope these 5 days will be very much fruitful for everyone attending these sessions. I am very much thankful to AICT for providing the grant to conduct this FDP. I am also thankful to our management, principal, and all other supporting staff for giving us the support and continuous encouragement to arrange these kinds of sessions. I wish all the best for all the participants for this FDP. Thank you.
Thank you, sir, for introduction of workshop program. Now I request Dr. D.V. Gevde, sir, Principal PVPIT Budgaon, to say a few words. Sir.
Thank you, sir. Good morning to one and all. I'm very happy and I'm getting privileged to welcome you all for this AICT training and learning program of computer science and biology under Atal scheme of Government of India. I'm very happy to welcome Dr. Sanjay Mahajani from IIT Mumbai, Dr. Yogesh Mahajan from Dr. Batu Loneri for today's lectures as a resource persons and for the inaugural address of this 5 days FDP. I am also proud to mention that Chemical Engineering Department is one of the best department of our institute, which has accredited by National Board of Accreditation up to year 2022. And we would like to work on the recent trends in industry and the various fields of research. As we know that we are now living in the era of Industry 4, and all our processes must be oriented to Industry 4. And therefore, there is a shift in learning paradigm, and Government of India is addressing all these issues through this Atal platform. So I'm very much thankful to AICT for sanctioning this FDP to our institute and showing the trust in our institute that whatever the responsibility is given to us, will definitely complete that responsibility to the maximum extent possible. And in the same lines, our chemical engineering department, HOD Professor U.S. Patil and his team have worked very nicely, and they have come out with a very good program which involves all highly well-known resource persons, and which will give a justice to all the topics which have been there in computational techniques in chemical and biology, which is very important nowadays, because all students must understand the mathematics involved in all these design processes in chemical engineering as well as in other allied branches of engineering. And therefore, to widen this understanding of the subject, the basics of all computational techniques, numerical methods is must, and that will definitely improve the quality of teaching. So I am confident that all the faculty members who have participated in this FDP will definitely get enriched through the techniques which they will learn and their actual application in the real life, which will definitely improve their quality of teaching as well as the understanding of the students. So it's very much important that we should be able to model biological systems, and ultimately our goal is to reproduce the biological systems as they are produced by the nature. And if we want to reach that goal, we as well as faculty members as well as the students must understand the basics involved in modeling of biological systems, their processes, which will definitely help to widen the knowledge perspective of all students. So for this FDP, we have received the good response from all corners of Maharashtra, as well as we have got a good response from all resource persons. And I am very delighted to know that Dr. Sanjay Mahajani sir is associated with us for this FDP. Again, Dr. Bhagwat sir from ICT is also associated with us for this FDP. Really, it is a very good opportunity for all of us to listen these well-known veterans in this field. And therefore, I extend all my best wishes for this FDP for 5 days. And I once again thank all resource persons for finding out their time and accepting our invitation to deliver the subject matter, the contents to all our faculty members which are participated in this FDP. So thank you and wish you all the best.
Thank you, sir, for your encouraging words and enlightening us. Now I request Dr. S.L. Bhagat, Professor, Department of Chemical Engineering, IIT Bombay, to introduce today's guest and speaker of session 1. Sir. Good morning to one and all. It is my pleasure to introduce today's speaker, Dr. Sanjay Mahajani sir, professor from Chemical Engineering, IIT Mumbai. He has completed his MTech in Chemical Engineering from IIT Mumbai. He has completed his PhD from UD City, Mumbai. He has started his career from Indian Organic Chemical from Khopoli. After that, he has shifted towards research at NCL Pune. Then he has worked with Monash University, Australia as a research fellow. He has lot of awards on his name. Amar Dicam Award, AICT Young Engineers Award, his Excellence Teaching Award from IIT Mumbai, PK Patwardhan Award, and he has lot of professional activities as a reviewer. He is also a member of Catalyst Society of India. He is a professor in charge at Tata Center of Technology and Design. He is a faculty coordinator for undergraduates laboratory upgradation at IIT Mumbai. He has also published 130 international publications, and he has 78 conference paper on his name. He has published one book and 4 chapters. He has on his name 5 patents which are granted. I welcome Dr. Mahajani sir to start his session. Thank you, sir.
Thank you very much. Thanks for that nice introduction. Am I audible?
Yes, sir.
Okay, great. Thanks. Thank you for inviting me to deliver this talk. I'm really happy to share my work, my knowledge with all the participants. If I understand well, all of them are from chemical engineering background or allied engineering background, and I will try and kind of be a bit general in terms of the content that I have in my talk, because this is the first talk in the entire workshop, and I was asked that it would be good if I give a kind of overview, okay, so that the following talks probably can go more in depth, and that probably makes sense and gives a right background and platform for further discussion. Let me share my presentation with you. Since it's Google Meet, I cannot see the chat box, but if you have any doubts or questions, you can always type them in your chat box, and within say about 5 or 10 minutes, I'll switch over to chat window and see the questions and try to answer them. I think it should be okay, right? Instead of, or if you want to stop me in between, raise your hand or unmute yourself and ask your questions as well. Okay, so I'm quite open to any of the ways of doing it. Only issue is when I'm presenting, I may not be able to see the questions if you type them in your chat box, because when I present, I'll be in a different window, and you are in a different window. So what I will be doing is every 5 or 10 minutes, or even whenever I remember, rather, I'll go back to the window and see whether there are any questions in the chat box. I hope this is okay, rather. I understand that many of you are teachers in chemical engineering departments at different colleges and universities, and I have tuned my talk accordingly. Okay, so I'm not going to go in too much basics in this talk because it's an overview. If you have any doubts, if you want to know more about my anything that I present, you can always contact me later as well to understand it better. I can share with you some literature on the particular topic, or I can discuss with you on WhatsApp, or even the e-meetings. Okay. So with that, let me start my presentation. I'll share my presentation with you now. and let me know whether it is working well. Uh, can you see the file?
Yes, sir. So
Very
we are
good.
able to see your slides. Yes, sir.
Yeah, fine. That's good. Okay, because now I'm totally in a different window where I can't see any of you, and neither can I see the chat box. So I'm just seeing the slides that I'm presenting. Okay. Uh, Fine. I have chosen this topic. Of course, it was not mentioned in the schedule because it was quite general in the beginning. But later on, I thought I would be specific in terms of defining the content of this particular talk. So, as the title says, it is 1 minute. I'll just try and use a cursor also. Um, yeah. As the title says, it is modeling, simulation, and computational complexities in chemical engineering applications. And that is quite close to the theme of this particular workshop, where we are talking about computational aspects of chemical engineering and biochemical engineering. I may not be able to give you give you examples of biochemical engineering because I'm not expert in that field, but I may talk or refer to biochemical engineering or biotechnology as and when it comes. Okay, but of course, I won't go much in depth. Okay. Again, just to let you know, I'm from Department of Chemical Engineering, IIT Bombay. But I'm there for almost 20 years now, and my areas of interest as far as research goes is reaction engineering, catalysis, process intensification, and energy-related applications. Okay, so these are my broad areas of research, and I take special interest in trying out different experiments at educational levels as well. And if somebody is interested, I can share with you uh, my experience on that also, but not as a part of this talk, but later. Okay. Fine. So with that, let me just go to the first slide. And again, it is very general, and I don't know whether you've seen this slide. And all the text and whatever I have written here is something that every chemical engineering student and teacher would know. Okay, because these are all subjects that we come across as far as our chemical engineering curriculum is concerned. Now, this is a picture taken from a very famous book from Mullain and his co-authors called Process Technology. Okay, and in that he's trying to actually show how chemical engineering field is complex. Okay, both in terms of scale and level of integration. So now you start with your first year, second year, where you have thermodynamics, which is scale independent. Okay, the first law of thermodynamics doesn't say that it is applicable only at a particular scale. That means, say, for 100-meter cube volume, and beyond that it deviates or something. It doesn't say that, right? So it is scale independent. Whatever you learn in thermodynamics is scale independent, and of course it is basic, so that there is no level of integration that's happening there. Now next you go to the transport phenomena course. Okay, this transport phenomena is also scale, I won't say independent, but the dependency on scale is very low. Okay, so we talk about differential equations, small elements across which we take material balance, energy balance, and so on. Okay, so again, transport phenomena course that we learn has nothing to do much with the scale. But since you have different processes to learning are coupled together, the level of integration is increasing. Okay, then comes kinetics and catalysis. Okay, where we have rate of reaction, and I will talk more about this because this happens to be my research interest. And so I've taken few examples from kinetics and catalysis to tell you about the complexities involved. Okay, so kinetics and catalysis, again, as you understand, it will be scale dependent, because for example, suppose you have a reactor volume of 10 meter cube and 20 meter cube, a batch reactor, you will have different conversion happening, okay, like or other different productivity that you will get, okay. At the same time, your catalyst particle size, if it is smaller or bigger, and if you have intraparticle diffusion resistance, then you will get different rates, right? So it is scale dependent, and at the same time the integration level goes up. When I say level of integration, what does it mean exactly? The complexity, okay. In simple terms, it is complexity or probably combination of various steps together. So okay, so now this is catalysis and kinetics. Then I'm not going to talk about every subject, but then you can very well understand that we have this interface technology, particle technology, unit operations, okay, like say distillation, evaporation, crystallization, absorption, stripping, okay, wherein you have even more level of integration, and the scale dependency is happening. What is the implication of scale dependency? That means suppose I do an experiment in laboratory, and I want to actually take it to a larger scale, say 10 times, 100 times, or 1,000 times. Will it get replicated very well? The scale up issues, okay, you may face some problems, okay, and that's why you have a scale dependency more in the case of unit operations. You have to consider mass transfer, how it behaves in different geometry or different scale of operation, what kind of Reynolds number you will get, what kind of say Smith number you will get, how will be the heat transfer, what is the mode of heat transfer that you need to have. So all these, no, like unit operations, and even the reactor technology, okay, that means what kind of reactor you will use, whether it will be multi-tubular reactor, a single fixed bed reactor, or there'll be interstage cooling, heating. So all these factors need to be considered so that it becomes more and more complex, okay, and of course definitely scale dependent. Now we are going to go to process level, okay. So this was still at the equipment level, this was at particle level or reaction level. Now we are going to the process level. The integration now increases further, and now the scale also increases. Now it is becoming a macro scale, MACRO, okay. And so that's how, like, we have courses like process control, process design, process technology, and so on. And finally what comes is operation, okay. That means you are actually operating the plant when it is installed, and day-to-day operation of the plant, wherein you really, now it is of course not at all scale, whatever is the scale, it's not going to change, but later you have to somehow make sure that you have the consistency in product purity and the rate of production and so on, okay. Of course, this is not a subject that we learn in chemical engineering. All these are kind of courses or subjects that we have in chemical engineering. Why I'm telling you all this? Because coming back to the theme of this workshop, like where we're talking about computational techniques, it all depends on the complexity. Let me go back to my title. So I say computational complexities, okay. So because you have so many steps happening together, okay, we need to really consider each one of them not independently but simultaneously, okay, and try to reflect that in some mathematical form so that we get proper insight into the process. I hope it is clear at this moment, okay. But just to elaborate this further and just to put that in proper context, look at this diagram again from the same book. I have taken this. This is your reactor, and you have at a particle level what is happening, at the catalyst level what is happening, the chemistry, molecular changes that are happening on catalyst surface, okay. So this is a different scale altogether. It will be micro, nano, or even molecular size dimensions, okay. That is what is happening on the catalyst surface, okay. Then at a reactor level you have a meso scale where you are talking about particles, reactors, reactor selection, and all that. And then you have a process when the reactor becomes part of the process, where you have so many other blocks which are connecting to each other in the form of a network, and which is nothing but process in our language, okay. So that is nothing but a macro level. So so in terms of scale, there are broadly 3 scales, but I will probably further fragment them in terms of modeling and simulation. So computational techniques as such, learning it independent subject, is one thing, okay, but that is more towards mathematics and numerical analysis. But if you look at the context in terms of whether chemical engineering or biochemical engineering, I think it's better for engineers to first look at applications and then learn kinetics. Oh, sorry, computational techniques, okay, because otherwise it is only mathematics, then there's no fun. Of course mathematicians would love to do it, but engineers will always look at applications, and then only they will be driven towards doing some maths, okay. So I think by this point it is clear. Let me go back to chat window and see if there are any questions. No questions so far. That means all of you are with me. Let me just check whether I am audible or not. Am I audible?
Yes, sir, you're audible.
Yeah, okay, thank you. I'll be asking you this question every 10 minutes, every 15 minutes, because today in this world of e-meetings, it's always better to make sure that we are well connected. Okay, fine. And let me know if my voice quality is not good or something, okay. And if it is okay, I will probably put my video off so that I'll get a better bandwidth. Is that fine? Or
Okay, sir.
yeah, okay, fine. Just give me a minute. All right, so I will go back to my presentation. Yeah. So yeah, let me move to the next slide. Okay, now there's some issue. When I switch window, it suddenly hangs. I don't know why it happens. I'll have to stop sharing and again start sharing. It's a bit tricky. I hope you are able to see this.
Yes, sir.
Thank you. So let's go to the next slide. Again, it talks the same language of scale and time. Now you have time coming in picture. I didn't talk about time before. Okay. So as far as chemical engineers are concerned or applications are concerned, look at it. We have a wide range of time and length that we consider. Okay. And I don't know. I doubt. Of course, no offense, but to any other branch of engineering. But just to tell you the uniqueness of chemical engineering, that we deal with such a big horizon, okay, wherein we have time ranging from 10 raised to -9, that is nanoseconds, going up to almost 10 raised to 6, that means of the order of years, okay. And look at the length scales. Like we go to almost 1 kilometers, and then we go down up to almost nanoscale. And you have come across these times and lengths in many subjects that you learn, and I'm going to elaborate that further as we go ahead. Okay. Now, when it comes to time, how do we have this particular range? Like, what are we talking about? How, like, basically, just take an example of reaction again. Okay, you can have very slow reactions, you can have very, very fast reactions. Okay, so let's look at this. In petroleum geochemistry, that means the things which are happening underground, like for example oil reserves, okay, or gas reserves, or the reactions, inorganic reactions that are happening in sediments, okay, they are happening over a long period. Okay, they are happening over a long period, and their reaction times are of the order of few decades, right? or even sometimes you have million years. Okay, how oil is formed? It is formed because of the reaction, right? Or like you have the biological either plant or animal material which is degrading over million years. Okay, and that's why you have crude oil and gas forming right underground, and of course coal. So these are the reactions, but look at the age, look at the time. Okay, it is tremendous. Okay, so that's why they are very slow reactions. Now what these numbers indicate are the reactivity. Okay, so reactivity is very low there, and under those conditions, rather at that temperature, pressure and all that. Then you have a scale where you have biochemical processes that are happening, and again you have the rate of the reaction going up, but not to that extent. Okay, and look at the reactions that are happening in industry, and where we're using catalysts especially. Sometimes the reactions can happen within seconds, microseconds and all. Look at oxidation. Example of ethylene oxide formation from ethylene on silver catalyst, nitric acid formed by ammonia oxidation, uh, methanol to formaldehyde. All the oxidation reactions so fast in the presence of catalyst that within second or microsecond or milliseconds you get entire reactant converted. Okay, so look at the scale that we deal with. Okay, it is not just that we want to do this. Okay, we can do this as well, we can do this as well. Okay, but then depending on the scale we need to have different of course the equations won't change, but the computational techniques may change. Okay, and your model may change, right? Model in the sense the assumptions that you make in your model would change. I'll come to that soon. Okay, I hope it is clear. Like these few slides in the beginning are meant for telling you that we are privileged. Okay, we are unique in terms of dealing with large scales and large time dimensions. Okay, uh, the kind of modeling and concepts that we learn in chemical engineering are able to capture this entire domain. Okay, uh, so let me go to the next slide. Oh, again, I have a problem. I don't know why it's. Oh, yeah. Okay. Uh, Now, I have posed some few questions here, and this is sorry, some of you probably would be knowing it, and maybe the repetition and too basic for you. But I was told that there are some students also attending probably this particular course. So let's start from scratch, and probably it is a good platform for further discussion that may happen in the coming lectures in this workshop. Okay. So let's try and understand what is modeling. Okay, of course I'm talking about mathematical modeling, I'm talking about modeling for engineering, and there is another meaning to modeling. Okay, I'm not talking about that. Okay, so what is modeling? I have tried to define it my own way. Okay, like, and of course you will have different definitions for it, but the essence will be captured everywhere. Okay, the same essence will be captured. Now what is it? It is mathematical representation. Okay, so this word mathematics is very important. Those who are doing modeling should be good in maths as well. Okay, I'm not saying that they should be, if they're good in maths they can do good modeling. Okay, they should understand the concepts also. The combination of understanding the basic concepts in engineering along with mathematics will make you a good modeler. Okay, right? So a mathematical representation of the behavior, okay, or state of a given physical system. It can be anything. It can be anything. Now it's a very general word. I'm not only defining this from the point of view of chemical engineering processes. Okay, it can be anything. It can be anything. So, for example, if I'm doing cooking in kitchen, okay, I can write a model for that. If I'm doing some exercise, I can write a model for that. Okay, anything. In mechanical engineering, you have turbines. You have compressors. So all these can be modeled. Anything that is based on some science can be modeled, and you have a representation, mathematical representation of the entire picture. Okay, in fact, we have a professor in our department who has modeled the entire, how when I eat something, okay, like how it passes through stomach and what happens to it, like all the processes are modeled mathematically. He has a first principle model of what happens in your body. Okay, so that is called system biology. Okay, like biosystem engineering. Okay, so modeling is a very general term, and anything based on science can be modeled with the help of maths. Okay, but the next line is also very important, very crucial. Model is written with an objective. Okay, it is aimed at achieving certain insights, keeping the application in mind. What does it mean? It means that if I have a system, I want to model it. Does it have a unique model? I'm taking a pause here. I'm taking a pause here purposely, asking a question. If you can unmute yourself and answer it, or whatever it is. But then the question is that if I am given a system, does it have a unique model?
No, no, sir.
Good, very good. I'm happy with that answer. So can you elaborate? Why not?
Because there can be various parameters and our objective may be different in modeling the system.
Excellent, excellent. Objective would be different. So that I like that word. The objective would be different. What I want from that model is important. Okay, and basically look at the next line, model assumptions, because whenever I write equations for a particular system, okay, we need to make certain assumptions. Okay, like for example, okay, like all of you know distillation. Okay, there's an assumption of constant molar overflow. Okay, what does it mean? That energy balance need not be written there. Okay, that means the maths, I'm reducing number of equations. My model is becoming simple. Okay, but then what am I doing by making that assumption? I'm compromising on certain behavior of the system. Okay, that compromise, whether it is allowed or not, it depends on what is my objective. Okay, if I want to get certain overall picture, okay, I can afford to make some reasonable assumptions and go ahead and make the model simple. Okay, so what does it mean? For a given particular system, now if I had time, I would have actually looked at just distillation and would have told you some 10 different models for a distillation column, depending on what you want from that particular system. Okay, but of course I'll touch upon this subject. Somebody else will cover in this course later probably. But what I'm trying to say here is the model is something that depends on our objectives and our assumptions. Okay, the assumptions will depend on objectives, and depending on assumptions, the complexity will vary and your computational efforts will vary. Okay, so suppose I have to solve some 20 equations simultaneously, which are coupled equations. It can be differential equations or all algebraic equations to be solved simultaneously. Okay, but if I make certain assumptions, the number of equations may reduce. Okay, from 20 it may come down to say 7 or 8. Okay, what is happening? My computational complexity is going down, and probably I'll get results faster, but at the same time I'm compromising on something. If it is okay, fine. Okay, like for example, constant molar overflow assumption, I'm compromising on what? I'm compromising on the variation in the flow rate in the distillation column. Okay, but if I want some broad or ballpark figure for how many stages I need for particular distillation or purity to be achieved, okay, in that case I can make these assumptions. I can do some quick calculations. Okay, so what I'm trying to say is, like, it is just a compromise or optimization between complexity and to reduce the complexity and and work with equations. Okay, so now so what is the use of model? And of course, this is another word that always comes with modeling. Okay, I don't know why it comes, but then yes, we always say modeling and simulation, okay. Why? Because simulation, of course, is something that is, I would call it as a tool. Okay, and that would take you take the given model and solve it. Okay, that's nothing but simulation. Okay, take a model and solve it. For what? Okay, so it solves it and gives you a virtual feeling that you are actually following the behavior of the system. Okay, that means you're doing a virtual experiment. Imagine, again, I'm giving an example of distillation column, commonly used operation in chemical industry. Okay, you have a column. If you solve the equations and simulate a column, what does it mean? On computer, actually you are virtually doing an experiment. Okay, as if like I'm sending the feed to a distillation column, I'm waiting for sufficiently long time to get a steady state, and what is happening at each plate or stage in a distillation column, what is happening at the top, what is the overhead product composition, what is the bottom product composition. Okay, so all these things, can be predicted without actually doing experiments, and that is nothing but simulation. But remember, simulation needs model. And again, as I told you before, model can be different for the same system depending on what objective I have in mind. Okay, so simulation, coming back to simulation, it is a virtual experiment. I'm going to come back to this definition of simulation again later, and will ask you some questions. Okay, now computational techniques, okay, they may play a very important role in solving simulation models of different complexity levels. I don't need to tell you this, very general statement, but yes, it makes a big impact. Why do we make assumptions? Because we want simple model. Why do we want simple model? Because we want to kind of reduce our computational efforts. Okay, so otherwise, no, predicting a particular behavior of a system through mathematics, it really needs large number of equations, and you'll have to wait for days or sometimes weeks to get the results, and people have been doing that. Okay, I'll tell you more about that. Okay, so it all depends. Okay, the scientists who really want to understand what's happening on molecular level, they will predict the movement of molecule, how the bonds are stretched, how the bonds are vibrating, all these things. Okay, so there's a purpose is different. Okay, there the purpose is not to use it for commercial purpose and take some action in the actual plant or something. It is for understanding the science behind it. Okay, so there you can compromise on the speed of calculations and all, and can wait for sufficiently long time to get the results. I hope it is clear. I will move to next slides. Okay, now again, as I said before, as far as scales are concerned, as chemical engineering, we have molecular scale. Okay, we have catalyst or particle level that we are. Imagine a reactor. Okay, for example. Okay, you are reaction happening, molecular scale, there can be things changing. Then at a catalyst level we need to predict something. Then at equipment level we need to predict something, that is reactor, say distillation column, extractor, pump, compressor, whatever. And at process level we need to do something, and the scale varies. Okay, molecule is of the dimension of the, say, nanometers or even smaller. Then you have process which can which can occupy the space which is of, say, 1 kilometer radius or 2 kilometer radius. Okay, it's possible, like you go to refinery, right? You have big processes. Coming back to reactor design, now this is again, I'm focusing more on reactor because, as I told you before, like that's my research interest. But otherwise also, reactor is heart of any chemical process. Okay, and every chemical engineer is associated with reactor. I think that's a general case study that we need to we can always take when we talk about subjects like computational techniques and all that. Okay, so I'm saying reactor design and simulation. So I told you that I'm going to ask you a question here, like what is the difference between design and simulation? So what's the difference between design and simulation? Can somebody unmute himself or herself and give this answer? A design problem and simulation problem.
Hello, sir.
Yes, please.
Sir, design is a specific plan we are preparing for a particular problem. Simulation is working on that particular design
Very
or
good, very good.
optimizing a problem.
Yes, excellent.
Hello, sir.
Yes.
Hello. Designing is to decide the process parameter up to the
Mhm.
limit, and simulation is to optimize the process. Uh,
Okay. Right. But I think go once, I see, I can go one step backward and give a basic definition in terms of uh, what is given and what is to be found out. Okay. See, because these are problems. So there is some input given and there'll be some output coming out of this. So a design problem, what am I solving it for? A simulation problem, what am I solving it for? Okay. So coming back to the first answer, I see it's like this. uh, I want to achieve certain duty. Okay. For example, reactor. I want to achieve certain conversion. Okay. I want to achieve certain selectivity. So this is a desired performance. Okay. That is given to me. That is the input. Right. That is the input. And what am I determining? I am determining the volume required. Right. Imagine those who are teaching reaction engineering, like this is a typical problem in third or fourth chapter of Fowler, right? Where I'm determining, say, volume or catalyst loading required to achieve certain conversion or selectivity. Okay, this is what problem? This is design or simulation. Yes,
it's a design. It's
perfect.
a design.
It is a design. Okay, it is a design. That means I'm determining the dimensions of the piece of equipment that will perform a given duty. And simulation is exactly opposite. Simulation is exactly opposite. What does it mean? There is a dimension given. Okay, you know what the volume of the reactor, you know how much catalyst loading you're taking. Okay, then you, if you provide the feed and with certain composition, you are predicting the performance. Okay, so performance is not given to you, performance is to be predicted, right? Okay, so it is basically virtual experiment that I'm doing. I'm actually going through the process. The plant is in front of you, column is in front of you, reactor is in front of you. Every minute detail of the piece of equipment is in front of you. You know that. And now I'm predicting its performance for given operating parameters. Okay. And that is nothing but simulation. But for both these activities, both the types of the problems, I'm not going to tell you more why, when it is design is useful, when it is simulation. You are kind of capable enough to understand what is the application of design and what is the application of simulation. What am I telling you here is, for both design and simulation, a model is necessary. A model is necessary, right? So I told you before also, simulation means solving a model, design is also solving a model. The mathematical equations may not vary much for the model which is used for design and the model which is used for simulation. What varies is the input and the output. Okay, that is important, right? Anyway, now coming back to the reactor, what do we need for reactor design and simulation? The first thing that I need is reaction kinetics. Nobody will disagree. Okay, without reaction kinetics, I can't design a reaction. I need to know how slow, how fast the reaction is, right? And without that, I can't design. It's a backbone of the reactor design. Is that sufficient? Is that sufficient? But before that, let's try and understand where this reaction kinetics will come from. It will come from laboratory experiments. I will do particular experiment under different conditions, and we have must have learned this differential method, integration method, okay, to derive the kinetic expression or the rate law for reaction kinetics, right? But what does it mean? That means you always have to do experiments. And engineers, okay, they are good at doing experiment, but you need resources, right? You need resources to do experiment. You need to set up a lab. You need to have analytical facilities and all that. So can I determine reaction kinetics by modeling? Can I determine reaction kinetics by first principle? Okay. Theory, understanding the reaction mechanism, understanding the reactivity of molecules, understanding what is the activation energy for a reaction without doing experiments. That is something, a field which is really catching attention these days, mainly because the theory, quantum mechanics, density functional theory, all these were there before. Okay, people had made advances and progress in theory much before than today. Okay, but what is happening today is we have computational facilities which are actually quite efficient, high speed computers which are able to do calculations simultaneously at different chemical computational platforms, and because of which our ability to solve the models has gone up, and we are able to do something. Do something means whatever I'm telling here, like we always think of reaction kinetics means चलो laboratory में experiment करो, data generate करो, and come up with some rate law based on that, right? What is the order of the reaction, what is the rate constant, what is the activation energy, and so on. But without doing experiment, can I have the same expression, similar expression, or more complicated expression, try and explain something? It is possible, but today, it is, as far as theory and overall modeling efforts are concerned, it is a gray area. I won't say people have not done anything, but there is enough scope to actually work in this. Okay, in order for this to come into mainstream, it will take some time, but sure, there are a lot many things that are happening. I'll briefly touch upon them in the next slide, if possible. Next, or probably in the following slide. Okay, so theory is also possible there, and you can do modeling, simulation, and computations to actually come up with rate law using theory itself. And if you're doing experiments, you can validate your model and in a better way. Okay, for the rate expression that you're coming up with. So whatever rate expression we use, R is equal to say K into CA, CB raised to 3 or 2 or whatever. So this is always a net effect, but actual reactions are taking place, actual events that are happening are many. Okay, and if you look at a reaction mechanism, the net effect that we write A plus B is equal to C is a result of some 7 to 8 steps that are happening as far as the reaction mechanism is concerned. Okay, right? So we have to actually look into that very well and understand how molecules behave, how the bonds behave, and we need to do a lot of modeling on that front. I hope you understand. We don't normally teach this subject in our curriculum, and yes, it is still developing, and it is slightly difficult and complex to understand. Okay, but as teachers, we should always appreciate that there are efforts going on this front, and once we come to a stage where this gets matured, I think there is so much load on laboratory is going to go down, laboratory experiment that's going to go down. At the same time, we will be able to select a nice catalyst, a perfect catalyst that gives me almost 100% selectivity towards the product. That understanding is important, and still catalysis is an area which is semi-empirical in nature. People just do screening of catalyst, ye try karo, wo try karo, and then after trying out some 100 formulations, they hit one formulation which works very well. Okay, and that working on 100 formulation screening efforts will go down once we achieve maturity in this area. Please try and understand and look at the importance of modeling in that. Okay, I'll come to that soon again. Then reaction might be hampered by mass transfer effect. Okay, if you have multiple phases present, like say gas liquid or liquid liquid, solid liquid, solid liquid liquid, so all these possibilities exist. Again, as I said, no, chemical engineering, like complexities, there's no limit to, sky is the limit, I would say, right? So mass transfer, like if one reactant is sitting in one phase, another reactant in another phase, okay, it'll always have mass transfer limitations, and we need to model them. We need to incorporate them in our model such that we have to see whether it affects the reaction rate or not, because sometimes the intrinsic reactions is very fast and mass transfer is slow. The overall rate will be governed by mass transfer and not chemical reaction. right? So we need to write equations for mass transfer as well to make sure that you have a right rate equation. What else? Reactor is accompanied by energy balance as well. Okay, you have heat effects for the reaction, and that would be coupled with your mass balance. Okay, it should be coupled. Why? Because the rate depends on temperature, and temperature is decided by the energy balance. So the heat effect reaction may be endothermic, exothermic. Heat may be evolved, or heat may be absorbed. Okay, accordingly, temperature may change. Whether you need heating or cooling system, all the decisions are to be taken. So energy balance has to be written. Then this is something that people find a bit uncomfortable most of the times. That is non-ideal flow patterns. That means you can't assume every reactor to be a CSTR or plug flow reactor. So now why? Because in reality the mixing may be non-ideal. It may be in between PFR or CSTR. Okay, I can't assume uniformity everywhere in my reactor at every position. Okay, I can't assume the radial mixing to be 100% and axial mixing 0. There are extreme scenarios. Why do you make those assumptions? Again, as I told you before, I want to simplify the model and get to some equation, and that may help me to do some ballpark or other back of the envelope calculations with less number of equations. Okay, so that's why I make assumption. But in reality, you may have mixing and other things happening, and people are working a lot to capture this mixing effect and non-ideal patterns. Okay, of course, we have 2 chapters in our Levenspiel or Fogler talking about non-ideal reactors and all that, but that is again at a preliminary level in comparison to what is happening today as far as computational techniques and computational algorithms have advanced. Okay, so I will give you one example regarding that, which comes from my own research. Okay, wherein we use computational fluid dynamics to predict flow patterns. Then about the pressure drop, most of the times for gas phase, you have pressure drop also affecting the reaction performance. Okay, that if you have a higher pressure drop, the density goes down, the concentration will get affected, the driving force of the reaction will get affected, and the momentum balance has to be written to actually get all this right. All this. So you have mass balance, you have energy balance, and you have momentum balance to be written together, and you have to have a model for that. Is somebody asking a question? Hello? All right, let me just go back to the or I would can I ask coordinator to kind of tell me if there are some questions in the chat box, then I will stop presentation. Is that fine?
Yes, yes, sir.
Okay. So at present there are no questions in the chat box, no? Because if I change the window,
No, sir. No, sir.
yeah, okay, fine.
No, sir. There is no question.
Yeah.
No
So
question.
if there is any question, just tell me, okay, so that I will stop.
Okay, sir. Okay, sir. We will inform.
Yeah, and if any participant has any question in between, also you can always unmute and ask the questions. Okay, not a problem.
Okay, sir. Okay, sir.
Non-ideal flow patterns.
Yeah. So any question on non-ideal flow patterns?
Yes, sir. How does it non-ideal flow pattern and pressure drop contribute to momentum? Contribute to momentum.
Oh, okay. They actually, it's the other way around. The momentum balance would contribute to pressure drop and non-ideal flow patterns. So I need to write Navier-Stokes equation in 3 dimensions to understand the velocity vectors and see whether you have axial mixing, whether you have mixing in radial direction, and so on. And similarly, the pressure drop is also included in Navier-Stokes equation. Okay, so it's the other way around. I need to write momentum balance to get all this, and mass transfer and energy balance. Again, you know the coefficients are function of Reynolds number. The boundary layer thickness also depends. So momentum balance is very crucial, and in fact, it is more difficult compared to mass and energy balance. balance because it has three directions like velocity, x, y, z, and that's why it's becoming more and more complex. And we tend to make assumption that we have one-dimensional model or at the most two-dimensional model. We don't go to three-dimensional model in our undergraduate curriculum because it becomes more and more complex in terms of solving it, and students won't really appreciate unless they get answers. Okay, they always first learn something which is relatively simple, and that's why all our textbooks, okay, normally don't consider momentum balance in our reaction engineering course. So it is decoupled from reaction engineering, but it is very, very important, as I said. Okay, so
Sir,
is that clear?
does the temperature difference contributes to this momentum balance?
Indirectly, because temperature will have effect on physico-chemical properties, right? Like,
Yeah.
for example, if I'm dealing with gas phase, that gas phase will density will change with temperature and pressure, right? So they will have indirect effect on yeah, indirect effect on momentum balance as well. So density, viscosity, they're all functions of temperature, right? So yes, they are coupled. So that's why now it becomes a try and understand. So what I'm trying to tell you is like the simple problem that we solve in textbook, how preliminary it is, how simple it is. What is the objective there? There also we are writing a model. What is the objective of the model? Objective of the model is to teach the concept to the students. Okay, that's the objective, and for that we are writing a model. Okay, that's why it is the simplest possible model. Okay, I just want to convey the theory. Okay, but in reality actually there's so many things happening, and if you really want to actually predict the things that are happening in real scenario in a plant, the reactor, how it is behaving, or I want to design a new plant and have a reactor design in that, then I have to consider all this to some extent. Okay, I can't just go by my textbook knowledge. Okay, that is what I'm trying to tell you. So that's where your modeling will come, simulation will come, design will come, different computational techniques, algorithm, all these things will feature. Shall I go ahead?
Yes, yes, sir.
Okay, so this is the complete picture as far as reactor is concerned, and this slide till, of course, I don't need to tell you, I very basic, like what is your reaction kinetics and all, but I thought again why I included this slide is just to maintain continuity in what I'm going to tell you later and what I have told you before. Okay, so what is this? This is I am not going to read this. Okay, this is all basic reaction engineering. Okay, you can see Arrhenius plot there, you can see rate expression there, you can see everything there. Okay, you can see activation energy, how it changes, sorry, energy, how it changes with progress of reaction, and what is activation energy, and this is nothing but activation energy. Why I have made this slide, because next slide is going to tell you how to calculate activation energy. Now activation, by the way, how do we determine activation energy for a given reaction? Most of the times we determine activation energy by conducting the reaction at different temperatures and plotting this particular plot. What is it? Arrhenius plot, right? And the slope will give me activation energy, right? So what it means is, like, I need to do experiments. I need to do experiments, but if I don't want to do experiments, at the same time I want to understand it better as to how to choose a catalyst, which catalyst will work better and all, I need to do modeling. I need to do modeling at molecular level. Okay, I need to understand what happens on the catalyst surface. I need to understand how molecules walk on the catalyst surface, how molecules fight with each other on molecule surface, catalyst surface, how molecules love each other on catalyst surface. Okay, so in order to know all this, okay, we need to write equations at molecular level. Okay, and look at this slide again. I'm talking about time and scale, which is on if you just go back to my earlier slide, this is a slide. I am somewhere here, okay. I'm talking about small size and small time, okay. Somewhere here, okay. Oh no, not here, sorry, here, here at this level, okay, at this level, right? So time and scale. So coming back to this slide, now there are many efforts that are going on. Okay, And what we are conversant with as normal chemical engineers is this, okay, where we are talking about continuum, okay. That means uh, I don't look at molecules. Do I look at molecules, how they behave, how they move, and all that? I don't see that. Whenever I write a model for a reaction or reactor, okay, I just write is a continuum space. That means everywhere. Suppose if you have a CSTR, at every point you have a molecule present. Both the molecules are present, A, B, and of course C. Okay, so I really don't distinguish between molecules. Okay, so that is our continuum model. Okay, but then if I want to understand the intrinsic kinetics better, if I want to calculate the activation energy and so on without doing experiments, I need to go to smaller and smaller scales. Okay, and this is again field on its own. Okay, it will take another 10 lectures to actually explain what I've given here. Okay, this is one figure that explains that puts together almost everything. Okay, so then again you have different scales there, okay, within your molecular level itself, and you can go back and do some calculations depending on what you want, what is your objective. So the smallest one that talks about femtoseconds and all, where it actually tries to capture the vibrations in the bonds, okay, translational motion, vibrational motion of molecules, then lateral movement and all. uh, it is actually done here, okay, and there are so many calculations that are done, which is nothing but a density functional theory, which uses quantum mechanics calculations. So it gives identity to every molecule, okay, that is present, and the bonds between the atoms that are present. Okay, look at what level we are going to, okay, as far as modeling is concerned. And there are softwares that are developed. Those who are interested in doing molecular modeling, those are interested in understanding how the reaction takes place on the catalyst surface, of course not just reaction for that matter, sometimes the properties of the components are also dependent on this molecular modeling. See, hydrogen bonding that takes place in water can be predicted very well using this. Okay, and because of hydrogen bonding, the boiling point of the water is very high. Okay, so that is so I can predict the boiling point of water without actually doing experiment and doing these simulations. Okay, so not just reactions, but reactions, like, it has tremendous demand, because you can decide which catalyst can be used under what conditions, and because of which you can actually get higher yields and required performance. So in terms of application, commercial applications also, it has a tremendous potential. But problem is, as we go down, the computational efforts go up like anything. So we have some faculty members in IIT who are working in these areas: micro scale, mesoscale. See, micro scale is actually looking at bonds, mesoscale is actually looking at clusters. Okay, and here also you have identity to molecules. Okay, so you are considering about 10⁴ to 10⁶ atoms, how they behave together. Okay, here in fact it goes down further. Okay, whereas in mesoscale you are looking at field. Okay, so only the kind of how your electromagnetic field is changing, and you don't have identity to the molecules in mesoscale. Okay, so all these three we haven't actually learned in our undergraduate program, but keep that in mind, and if you're more interested, I can pass on literature to you, and there's a lot of work going on in this field. Okay, and why it is happening, not just to predict the rate equation for a given catalyst, but to identify a catalyst for a given reaction. Okay, it's very important. You can imagine today at this stage also, I gave you example of ethylene to ethylene oxide reaction. You can't go beyond 15–20% conversion in oxidation reaction. Why? Because you have side reactions taking place, right? Many oxidation reactions, side reactions is a problem. If you get right catalyst, you can avoid those reactions. And if you can go from 20–25% conversion to 80% conversion, look at the impact that it will make. Okay, your catalyst or your reactor size will come down drastically. Okay, your process will get compact and cost effective. Okay, and that is the prowess, that is the potential of modeling, simulation, and computational techniques. Okay, it's very, very important that we should look at this at least, okay, if you don't practice it, because it needs high efficiency computer machines. Okay, so we have people who, we have students in IIT who are working in this, they just run their program for weeks together to get the answer. Okay, and what answer they get? Okay, fine, after 3 seconds what will happen? Okay, so it's like after waiting for about 1 week, they will predict what happens in 3 seconds. Okay, so I'm just giving you some numbers to tell you how complex it is and how computationally expensive it is, right? So this slide summarizes everything as far as the computational efforts on molecular level is concerned. I don't want to get into detail, and since I'm not worked in this area that much, I don't want to give basically I don't have examples here to explain. Of course there are many examples in the book that I could have done it, but I thought I'll spend more time on the other scales wherein we have some examples to show you, and I can explain them better because of my expertise in that area. Okay, so let's go ahead. Simple. CSTR, PFR, batch reactor. Now this is something that we do. I told you these are models. What I have written on the right hand side, though they're simple equations, unknowingly we are actually writing a model. These are all models, by the way. This is a mathematical representation of CSTR. This is a mathematical representation of PFR. Okay, right? But why we are able to do it in such a simple manner? Okay, it doesn't look like a complicated set of equations, algebraic or non-linear algebraic or linear algebraic or differential, ODE, PD and all that. Why? Because we have simplified them. Try to understand the role of assumptions here. Okay, now in this we need to know the rate of reaction. This term is very important, and for this term, just now I explained to you lots of things are happening at molecular level to get intrinsic kinetics, but intrinsic kinetics, as I told you before, will be hampered by some other effects which are happening at particle and bubble level depending on what kind of reactions you have. So reaction with mass transfer and heat transfer, reactions in solid, for example in catalyst or reactants, you have intra-particle effects that are important. Okay, those who are teaching reaction engineering probably would have dealt with effectiveness factor, Thiele modulus and all. But remember, there again we make assumptions that the reaction is first order and all that. If the reaction becomes a second order or reaction has 2 reactants and all, then defining effectiveness factor is difficult. Okay, so you have to write equations and actually solve them together. Model becomes more and more complicated. Gas liquid mass transfer, if you don't have solid, but if you have gas dissolving in liquid, there again you need to write all this film theory or some penetration theory and come up with equations to solve for rate of reaction. Why we are doing all this? Because we want to get this particular rate in our equations. Okay, exact value of this rate, realistic value of this rate. It may not be intrinsic kinetics. Sometimes it may be hampered by mass and heat transfer effects as well. Okay, let's move to the next one. Okay, where we are talking about mixing related issues. Remember that slide where we're talking about mixing, non-ideal flow patterns. Okay, they are very important. Okay, they are something that we normally tend to ignore. Okay, when some students come to like our reaction engineering course, like last year I asked some MTech student, okay, like, do you know RTD, residence time distribution, E curve? नहीं सर, सुना हुआ लगता है, but वो ऑप्शन के लिए रखा था. So that's the answer we get typically. Why? Because it's slightly difficult concept to understand. Okay, but it is very, very important. Okay, CSTR and PFR is just basic. Okay, it is not going to help you beyond a limit if you really want to design a reactor for commercial applications. Okay, we need to understand the non-ideal flow patterns very, very well. And why are they important? Because there are 2 types of effect: micro mixing and macro mixing. Okay, I'm very sorry, it should be other way around. First is micro and the other one should be macro. Okay, In micro mixing, MI, you should read it at micro mixing, and this is macro, because the explanation given here is for micro mixing, right? It is relevant when reactions are very, very fast. Look at combustion for that matter. It's such a fast reaction. No, if a hydrocarbon comes in contact with oxygen, the reaction will happen within no time almost. Okay, but that contact has to be established. Okay, so that at molecular level, that contact is not happening. The rate is not dependent on the reactivity. Rate is dependent on how well the mixing has taken place on molecular level. See, molecular level mixing is different from the macro mixing. So this is macro mixing, MACRO. Read this as MACRO. I'm really sorry. I just realized when I flashed this slide. Okay. So it is sometimes no, you when you take the sample out from a reaction mixer and analyze it, it is going to give you the average value. Okay, but it is not going to tell you whether there are any gradients at molecular level. Okay, so that is micro mixing. Okay, and macro mixing is at a reactor level. For example, near the feed you will have one concentration, and somewhere in the corner of the reactor you may have a dead zone, and there you will have different concentration. So I can't make the assumption of CSTR there, right? So that mixing is at a macro level. So there are two types of mixing which we need to consider, and in both the cases we need to know the local velocity, we need to know the turbulence level, energy dissipation rate, and many state variables locally. Okay, so for example, in a CSTR, I don't need to know here what happens, here what happens, here what happens, because everywhere the concentration assumed that is going to be same, but in reality the concentrations may be different. Okay, and that's why I need to have the local values of all the velocity vectors and temperature, pressure, state variables, and everything. Okay, similarly in PFR, I assume, okay, that along the radial direction there is no concentration gradient. There is no concentration gradient. I am assumed it, but in reality it maybe there may be parabolic profile or some other kind of profile, and need to consider that, because actual performance will not depend on your assumption. Actual performance will depend on what prevails in reality, right? So that is what I was going to tell. Yeah, right. So any questions so far?
Sir, still there is no question in chat box.
Okay, very good. Okay, there are no question. That
Hello,
means
sir.
yes, yes. Okay, go ahead.
Yes,
Yes.
sir. I would like to know whether in macro mixing, can you determine the gradient? If it is
Yeah.
there?
So micro mixing at molecular level, if there is a difference there, okay, that actually with first principle equations, it is slightly difficult, okay, to understand the concentration gradient that is happening at a molecular level. So it's a good question. There are efforts going on. So basically, again, we need to go to molecular modeling in the reactor. Earlier, the molecular modeling that I explained was on the catalyst surface. Okay, right? But now we are talking about reactor in which the molecular level mixing is inefficient. Understanding that there are papers, there is research work going on, but again we need to take help of molecular modeling along with the macro level modeling. Okay, so but then there are indirect ways to deal with this. There are ways to actually incorporate micro mixing effects, and there are some empirical and semi-empirical models that are available to actually take care of this mixing effect, which superimpose on actual rate of reaction. So for example, now I'll tell you, suppose you take wood, okay, and burn it, and then pass air on it, air over it. The rate at which wood burns, it is not the intrinsic rate of oxidation reaction. Why? Because the mixing is not happening properly. Okay, because you have a flame and your oxygen concentration, oxygen is one of the reactants, right? That concentration varies along the spatial coordinates in the flame and around the flame, right? And that is very important. Okay, and that mixing will actually govern the rate of reaction at molecular level. Okay, or molecular level mixing is going to govern the rate of the reaction. And to determine that, actually, there are some semi-empirical models, as I told you before. Okay, but still, first principle model at that level, people have not yet attended to that extent, because it is computationally very, very expensive.
Very different. Yeah.
Yeah. As I told you, people are still trying at catalyst level with some 10,000 or 1 lakh atoms. Okay, whereas in our combustion in the reactor, you can imagine how many atoms will be there, multi-million atoms. Okay, so it is difficult to actually first principle get a first principle model and determine those gradients. But it's a good question. Yes.
Okay.
Any
Sir.
other question? Okay, good. So let me go ahead. I don't know, how are we doing on time? Can somebody tell me? Like 1 minute. Let me just check. So we still have 1 hour to. No, how much time we have?
Yes, sir. We have time till 12:15, sir.
12:15. Good, good.
Yes.
Okay. So what I will do now, I will probably, I don't know, continuously talking for 2 hours is not a problem for me, but for those who are listening to me, they will have some issues. Okay, it may become boring. Maybe we can take 5 minutes break in between. But let me cover before that this important aspect. Okay, a case study. Okay, is that fine, or you want a break now? Shall we take a 5 minutes break?
Sir,
Yes, sir. Yes, sir. We'll take
sir,
5 minutes break and then
Yeah.
we'll join once again at 11:15, sir.
Okay, fine. Great. Okay. Let's
Yes,
meet
sir.
at
Yes.
11:15.
Again,
Right,
we'll
right.
start at 11:15 sharp, sir.
Okay. Thank you.
Okay, sir. Okay, sir. Thank you, sir.
Shall we start?
Yes, sir, we start.
Are you able to see the presentation?
Yes, sir, yes, sir. Presentation is there, sir.
Okay, great. And you can tell me, like, if I'm going fast or slow, because then I can adjust my overall content accordingly. Yeah? Is the speed okay?
Yes, sir, yes, sir. No problem.
All right. So I'll just assume that it's okay with all others as well, and we'll maintain the same. And let's see, because the time, of course, is a constraint, but then you should not just cover the entire portion within small time, so that we really don't digest much. Okay.
Yes, sir, yes,
Because
sir.
what is going to come later now is slightly advanced. Again, I will try and simplify it as much as possible. So far, whatever we discussed was basic in nature, something that we knew. And of course, whatever I'm going to discuss will also something that you might be knowing, but it is at a next level. Okay. Uh, Coming back to the earlier slide where we stopped, we were talking about mixing related issues. How do we consider this non-ideal flow pattern? How do we get local velocities? How do you get local turbulence level? How do you get energy dissipation rate at a particular point? What would be the temperature, pressure, concentration of species at a particular point? Okay, and that too over the entire geometry. I have a reactor of, say, suppose 10 meter cube volume, and everywhere I want to know the concentration and velocities and all. Isn't it going to be a problem? Yes. And it is something similar to the molecular level modeling, that I need to now divide my reactor in almost million cells, and every cell has to be considered as a kind of differential element and right balance across it. So what you see in this slide is a new technique. I won't say new. In fact, 20 years back, 25 years back, it was new, and now everyone knows about it. But then, of course, again, still it has not come to undergraduate level. So that's why I'm calling it as a new. It is nothing but computational fluid dynamics. I call it as a revolutionary tool for modeling of flow patterns. I remember when I joined as a faculty member in IIT Bombay in 2000, that time it was quite new, and I happened to actually conduct a workshop on CFD. And that time and today we are here in 20 years. It has really revolutionized the entire modeling business in chemical industry. Okay, and now it is being used for many applications. Okay, and that time it was just considered as something new coming up. People were saying, no, it's not going to be useful, it's going to be computationally expensive. Why do we do that? We already have correlations. Why do we need to know velocities and all? So but then now, because the 20 years, not just we have made advancement in modeling techniques, we have very high efficiency computers also coming up. Things are becoming very easy. Okay, so I had my student that time working on a CFD problem. Used to get frustrated because of the computation speed of computers. The same problem today is solved by a new student within no time. Okay, so so that's the things that that have kind of happened in last 20 years. Okay. So what are these equations? These equations are nothing but, okay, let me just go back, pointer option, there's a pointer, yeah. So these are continuity, momentum, energy balance equations, and they are to be solved simultaneously. Try and understand this simultaneous. I'm using the word simultaneous, they're coupled with each other. I can't solve them independently, one after the other. Okay, and when it is coupled, then the computational efforts go up like anything. And secondly, look at these equations. Okay, what do you have? You have all these PDEs, partial differential equations, and in that there are source terms, okay, which are non-linear in nature. So you may have somewhere square or something happening. I'm not included a reaction in this. Okay, in your species balance is also not included. Okay, you'll have equation for different species. Suppose you have 10 species, you'll have 10 such equations, and every equation will have a source term that will have reaction term, which may be non-linear in nature. Why I'm telling you all this? Because the computational complexity is at its speed here. Okay, that means there are so many equations, that too complex equation, coupled equation, non-linear equations, partial differential equations. So imagine any complexity and it's there. Okay, so what I'm trying to convey to you is that still we have overcome this limitation over the last 20 years, 25 years, and today we are able to do this calculation with a reasonable speed. Okay, of course, again, it depends on non-linearity. Sometimes you have to wait for days or something to get an answer, but that is fine. Okay, that is fine. If, but then the information that you're getting is highly valuable. Imagine in a reactor, at every point, if you're getting velocity, concentration, temperature, pressure, you're almost captured everything about that reactor, the way it's behaving and all, right? What else you need? But again, there are some simplifications that we need to do just to compromise on speed and all. Again, coming back to this interplay between computational speed and accuracy and objectives expected, right? So this is the answer to my earlier question, where I need to know the local velocity and local attributes in a reactor. Okay, CFD is becoming very important, and now I have some case study here. I have some example here from our own research, and you can imagine. Sorry, I'll just explain you the application. What I'm trying to tell you here is underground coal gasification, UCG. This is, you won't imagine, like, okay, this is something that can be done with chemical engineering very well, okay, and with the tools like computational fluid dynamics and all that. Okay, this is not a conventional reactor. Okay, what am I doing? There is a coal available deep underground at a depth of about 500 meters or so, right? And I can't mine it. I can't take it out to the surface. So what is being done is you drill injection well, you drill a production well, you connect them horizontally. There are ways to do that. Oil companies which produce oil have kind of mastered these techniques. Okay, and this connection will establish some flow to happen. Okay, then you pass your gasifying agent like say steam and carbon dioxide and oxygen and so on, and in the coal seam itself the reaction will take place and the product will come out in the form of carbon monoxide and hydrogen, and that will be taken to gas cleanup and CO2 capture, and then you have electricity generation, the power plant. Okay, we have very large reserves of underground coal to the tune of 60 billion tons. Okay, so if you are able to do, we in the sense India, okay, so if you are able to do something effectively here, okay, then you have so much energy available and will be almost self-sufficient in our energy demands for power generation. Today also we have surface coal available, but it is high ash coal, and deeper you go, many places ash content goes down. Okay, like we have many mines or seams available, especially in Gujarat, where you have lignite and all, and if we are able to kind of get this going, it's really beneficial from country's economy point of view, because energy is something that decides in economy for the industry, directly related, and the CO2 generated can be put back to the well. Okay, so this is the application. Now coming back to our main theme of modeling, simulation, and complexities in computations. Now this is a reactor. This is a reactor. How will you model it? Is it a PFR? Is it a CSTR? No. The flow patterns are non-ideal. And this reactor is growing with time because coal is getting consumed. Okay, and imagine what can happen inside. So a lot many things are happening inside, and this was a project given to us by ONGC, and they asked us to actually try and understand it better. So we did experiments, we mimicked these conditions in laboratory, and finally came up with a model, okay, which is a combination of CFD and our conventional modeling approach. And we are now able to predict what will happen if somebody gives me the coal sample. I can find out the composition of a gas that comes out. I can find out the flow rate of the gas that comes out. I can tell you how much coal is utilized, how big is the cavity that is generated there. Okay, so all these predictions are done, okay, using this model that we have, and that simulator has been passed on to ONGC. So this is a typical process. Now I'll just look at a coal seam. Okay, above this you have a non-carbonaceous material and all that. This is a coal seam. You have gas going in and gas coming out at any given time. This is the picture. This is the cavity that is generated. Okay, now what is going to happen is, because of the high temperature, you have a roof of the cavity. The coal is getting detached from the surface, it is falling down on the cavity. Here you have the ash, because some of the coal is burnt and energy is generated. That energy is used for gasification, and this is the coal which is unreacted and getting reacted because of the gas that is coming out, and carbon monoxide and hydrogen is going to the product well. Okay, sorry, I'm going a bit fast because that is not important. I'm not here to tell you what underground coal gasification is all about. I'm focusing my attention on how we did modeling of this process. Okay, but you can imagine, you can't assume this as a CSTR, you can't assume this as a plug flow reactor and so on. So how do we tackle this problem? This is a great challenge now. Okay, so if you want to do process modeling, what data you need? Okay, first of all, reaction kinetics, the same thing that I showed you before. Look at it as a reactor. Okay, then reaction kinetics is required, heat and mass transfer is required, flow patterns are required. This is very important. Okay, and this is what I'm going to tackle. That's what I said, no, non-ideal flow pattern. And of course the thermomechanical failure, which is something very peculiar to this process. Why? Because you have this coal falling down. Okay, that also needs to be captured in the model. Okay, so these 4 inputs are required for UCG modeling, which is going to give me the output in terms of cavity shape and size at any given time, and a product gas composition. Okay, and if I am able to predict it, imagine I don't need to really do many experiments, and they are expensive experiments. I reduce lot of burden on my pilot plant expenditure. Okay, and that's the utility, that's the potential of this modeling. Okay, entire modeling. We generate kinetic data in laboratory, we include the mass transfer effect, and we get time versus conversion and come up with the kinetic rate equation. Okay, done. Okay, I don't want to spend more time on this. There's an instrument like thermogravimetry analyzer and all that. So just for the sake of completion, I'm just including this side because kinetics is determined using CO2 or even water. Okay, for gasification. Intrinsic kinetics is known. That's the input that's given. Okay, heat and mass transport effect are also calculated. Now comes is the main thing, that is velocity contours at for all cavities. All means at different time intervals. This is a smaller one, then it is growing. Okay, right, at different times we are generating them. Look at a date 2010. This is the work that we did 10 years back. Okay, today we still have even more advanced computational techniques and all. Okay, we have different zones that are generated. What does it represent? Okay, what does it represent? The velocities at different time, at different places in the cavity. I've just taken cross sections. The blue one is the velocity, which is very, very small. The red one is very high. Okay, and the white one is a location or a space where velocity is even higher than this red color. That's why it is not showing up. Okay, so look at this, how it will get evolved over time, and this is what we were able to predict. And not just velocity, we were able to predict temperature, we were able to predict, so all these things, like so. But then of course this is reaction is not enabled. If you enable reaction while doing simulation, then your computational time will go up like anything. How did we arrive at this equation? How did we arrive at this particular velocity profiles? By solving these equations. Okay, of course with modifications in terms of geometry and all, giving right boundary conditions and so on. The set of PDEs, algebraic equations, differential equations, coupled equations solved together. Okay, how much time it takes? Enormous. Of course it was done in 2010. The student had to wait for a couple of days, 3 days, 4 days to get the answer, and at the end of 3-4 days he's desperately waiting for answer and realized that he had made some mistake in giving input. You can imagine how depressed he will be. Okay, he just lost 3 days, right? So this is a problem, but today we are able to do this in almost less than a day. Okay, that's how the computational speed has gone up. The software also has become quite efficient now. They have more robust and fast algorithms which are able to do these calculations very, very well. Okay, So now why have we done this? Because we want to understand what's happening inside. I can't treat it like a CSTR. I can't treat it like a plug flow reactor. Now how do I predict the conversion? How do I predict the concentration of the product in the gas that is coming out based on this? So that's why we came up with an exercise which is very important. And this is something that one should understand how to actually come up with a model which is simple in nature based on the flow patterns that I have generated using a complex computational technique like CFD. Okay, so after getting this flow pattern, what we did was if we enable reaction in this and try and come up with a first principle CFD model, then you will take hell amount of time. Okay, it will take more than week or even sometimes couple of weeks to get the answer. Okay, just to simplify that, what we did is like we looked at this is called the compartment model approach. What does it mean? It means that I look at this velocity profile, and by looking at this velocity profile, I actually imagine this entire geometry, this geometry as the network of my basic cells like PFR and CSTR. Okay, now there is a technique to actually come up with the right network of these cells or network of these ideal reactors, which will represent the behavior like what we get here. Okay, now so what is common in this network and this? The common is that the residence time distribution, the E curve that you get. Okay, the E curve, that means if I send a pulse here, send a pulse here of some dye, if I inject it here, the way it comes at this point, it is going to give me some E curve. It is going to give me some E curve, and that E curve has to match with the E curve of the real geometry that I have simulated here in CFD. Okay, right? And if that is matching, that means I have got a simplified compartment model. This is called as compartment model. Okay, and this compartment model that can be used quite effectively to predict the reaction conversion. Let me repeat, there are two approaches. One approach is a basic approach, a first principle approach, reaction enable approach, where I put all the equation in CFD and try and solve it, but it is computationally highly expensive, may be used only for validation. Okay, I can't keep doing it. Okay, that means if I want to see the effect of parameters, suppose I change that inlet temperature, what will happen? I will have to wait for 3 weeks to get the answer. Okay, if I change the flow rate, what will happen? I'll have to wait for another 5 weeks to get the answer. Okay, I don't want that, right? So it may be used only once or twice to just validate the results of my approximated model called as compartment model. Okay, so this is my compartment model, and we actually verify that, and the results are quite similar. Okay, yeah, any question? Hello? Maybe I will stop after I complete
No,
this
sir.
case
No,
study.
sir. Yes, question is not there.
We'll continue, sir.
Yeah,
And
okay.
then we can discuss.
But yeah, I'll stop after this case study and take up questions. And if something you're not understood because I've probably gone fast, okay, we will come back to that. Okay, so so look at this. This is my actual geometry. Okay, actual geometry. You have void, you have coal seam, you have some coal that is fallen on the floor of the cavity, you have ash collected here, right? So we approximated it as this. Okay, because when you have to model it, like you have to make some assumptions, right? So we did it this way. And then by solving this compartment model using, this is my compartment model rather, that has a basis of CFD. Okay, we were able to get the profiles, the calorific value, how it changes with time, then mole fraction of individual gases like hydrogen, carbon monoxide, how it changes with time. Okay, there are three different profiles here. Of course, I won't elaborate much. One is without considering spalling. Spalling means what? Spalling means this. Okay, that means the particles which are falling down. Okay, if they fall down, they create fluctuations. Okay, in the actual gas. If you don't consider spalling, then it is a very steady, smooth profile. But if you consider spalling, see, this is what is happening. this falling taken place, the composition come down, start increasing again, this falling takes place, and so on. So you see some fluctuations there. Okay, so we were able to capture that as well. Okay, so what I'm trying to tell you here is that such a complex problem can be tackled very well using computational techniques, but with some creativity in terms of this compartment model to reduce the computational efforts. We have machines, we have algorithms, but they themselves have limitations. How many cells did we make here? The entire geometry. This is 1 meter cube geometry. Okay, it's not very small, not very large also. Okay, but within 1 meter cube, we had more than million cells for which the calculation was performed. Okay, right? And with that, we got all these contours or velocity field. Okay, and then we captured that velocity field in a simplified model that can be solved using MATLAB or something, and we are able to get this behavior which is reasonably good. And this is the value of calorific value that generally obtained experimentally also. Whatever field trials were done in the past, they got a similar value of about 150 to 160 kilojoules per mole. That's a calorific value. Okay, and we are able to predict it very well, right? And overall, I think we were able to capture almost all the effects. Okay, so that is the potential of modeling, simulation, and computational effects or other computational techniques that we have. Okay, and it is changing very fast. Don't worry about computational speed today, because after 5 years you're going to get a double or even more than that computational speed. So at the time we did this simulations, we were worried so much about speed of computer, but today I think same program runs in the computer at almost half the time. Okay. Now I will take a small break in the sense, if there are any questions on this particular case study where I have tried to tell you about CFD, its use, and how we have used it for chemical engineering applications. Okay, any doubts on this before we go ahead?
Sir,
Yeah.
sir, one question is there in chat box. I will ask.
Yeah,
Sir,
sure.
the question is like that: how the space volume is divided in compartments? Are they considered for CSTR or TFR?
Yes, good. Yes, how it is done? I'll answer the second question first. Yes, they are CSTR and PFR. Okay, for which I can write simple equations in MATLAB and solve them. So these are all CSTRs. These are all CSTRs of different volumes. These are all CSTRs of different volumes, and these two are plug flow reactors. Right. So this network is such that the flow pattern that we get is exactly similar or very close to what we get in reality. Okay, right? So that is the answer to your second question, that they are the networks of PFR and CSTR. Now the most important and a very good question is that how do we arrive at this? How do we arrive at this? Why 3 CSTRs? Why 5 CSTRs here? Why five CSTRs here? Why 2 PFRs here? Like, how did we arrive at this? And I was expecting this question. Okay, there is no particular algorithm to arrive at the compartment model. Okay, so it's not like blindly just follow some algorithm and you get this compartment model. You have to try out different options and try and visualize this particular velocity field, and then try out different options and see for every trial and error whether the E curve that you get for this network, E curve, that is residence time distribution curve, that you get for this network is matching with the E curve that you get here. Now CFD is able to give you the E curve. So there is option in the software, like there are many softwares like ANSYS, COMSOL that can be used for this. Okay, earlier it was called as Fluent. Okay, you can see this name here, Fluent. When we did this is a 6.3 version of Fluent that we used. Now it is called as ANSYS. Okay, the same software with some modification. Now it's available commercially. Okay, so we can generate E curve there is an option there, like it will put a tracer and do some calculation for a tracer by freezing the velocity field, and will tell you what the E curve will be there for this particular geometry. And the E curve for this compartment model, I can generate myself by writing equations, okay, and solving them together. Now, this E curve that I get for this compartment should match with the E curve for this particular geometry. These of course at different times, okay, and with respect to time, the volumes of this CSTR and PFR will change. So that way we did this mapping and comparison of E curves and arrived at this particular configuration. It took some time. Okay, it took some time. We tried this out, try that out. But how the basis for this is, okay, I can see some velocity vectors, how they're moving. Okay, for example, oh, I should have shown that the velocity vectors like this are obtained by actually solving equations, and you can see there is a circulation happening here. So that means there will be a big CSTR type of behavior here, right? There is this channel here, tubular flow happening. That there may be some PFR there, okay, and there is a small PFR in this portion as well, because when circulation happens, then this particular stream goes like this here, okay. Though this arrow is shown here, it actually, if you just go close to the wall, there is another PFR, okay. So you'll have many CSTRs and PFRs combined with each other, and you get this behavior. So you see, this is a PFR, this is a recirculation PFR, this is a main PFR, which before the tracer comes out at the outlet, okay, you have some time lag happening, and that is represented by this PFR, okay. So just to give a short answer to your question, how do we arrive at this? Of course, we need to do a lot of trial and error, and it is not just a blind trial and error, it is based on the flow visualization that we have from CFD. Is that fine? I hope I have answered your question.
Yes, sir. Thank you.
Okay, thanks. Any other question?
Yes, sir.
Okay. Yes.
So, as we have discussed related to the pilot plant, but how modeling and stimulation will be helpful in cost reduction when we are doing construction any plant on the major level?
You mean the commercial plant, right?
Yeah.
Actually, okay. Actual level modeling simulation, as we've seen before, see that okay, so let me just try and instead of answering short, let me just try and tell you how this entire process development is done, and what are the different activities before we go from laboratory to the plant scale, right? So what happens is you actually do some experiments in lab and come up with a process know-how, okay, and you have small apparatus in which you conceptually prove that, okay, the reaction is working well, catalyst is working well, these are the conditions for downstream processing, I get so much yield and all that. So that is laboratory know-how, which is documented, and now that is given for engineering, okay. So the next step is people say, fine, yeah, this is good, and before we actually, engineers will actually look at all the information data given, come up with some kinetic models, and try and simulate the performance of the process, okay. Now somebody who is investing in it would say, what's the guarantee? Okay, I want to actually see it happening at a small intermediate level, okay, because if you want to scale it up from some few grams to few tons, okay, that's very risky, especially for non-conventional equipment like reactor and all that. Distillation columns are matured, okay, like people know if it is working in laboratory, it will work in actual commercial plant as well, okay. So so there is a demand that the scale-up factor should not be more than 10 or something. So we should have an intermediate scale where we actually have a pilot plant, and we do some experiments in pilot plant, generate the data, generate confidence, and that can be used further for designing the commercial plant, okay. So this is the overall activity, and once the commercial plant is designed, it is commissioned and operated, Okay, now where is the modeling simulation helping? So whatever I've explained so far, like first thing that I talked about is the modeling at catalyst level. So getting a right catalyst for the reaction to get more yield, so that at laboratory level also we are looking at a know-how, the investor should get convinced that okay, somehow the cost is relatively low and I can get more profits. Okay, so so getting a right catalyst, doing some simulation at molecular level, it helps. Okay, then second thing is like your reactor design and other things. So as I said before, like sometimes the unconventional reactors, like reactors will have different kinds of geometries and all. Okay, and the complexity involved is quite high. Okay, so in laboratory sometimes we don't realize that, because heat transfer effects for that matter, the surface area per unit volume available in laboratory is very high for heat transfer. So heat effects are not evident in laboratory, but when we actually do it on a larger scale, like you will realize that okay, so much heat is generated in my reactor, reaction mixture is becoming very hot. Okay, that means there was some cooling required. So all these calculations are required to be done, and people do that, right? Okay, so that's why they, and if you model it very well, then it is really good, and you don't need to really do so many trials on pilot scale, because you are already have a basis that is coming from the model, and your pilot plant design becomes very easy. Okay, now still there is some uncertainty. Okay, like that you want to go from pilot level to the commercial level. It is not that if everything works on pilot plant level will work well for commercial level. Okay, now this confidence will again come because of model. If my model was able to predict the transition from laboratory to pilot very well, then the same model can predict the transition from pilot to commercial level very well. Okay, so the model provides basis, it gives you confidence. Okay, the same model, I just on computer I need to change numbers. Okay, and come up with the plant design. Okay, of course with whatever experience that we have gained in pilot plant. Okay, so that particular step is also important to generate more confidence. It may not save much, of course, definitely sometimes from pilot to commercial scale, some of the areas still uncertain, you can do some modeling. Okay, but what is more important here is that my model has worked very well for pilot. It is again tuned to the data that I get from pilot, and that can be used further for commercial plant simulation. Okay, so that is another use of model. Second thing, now I am coming to this. In fact, this part of the talk is dedicated to that, where the use of modeling and simulation for commercial plant. Now, designing the commercial plant, of course, we need to do flow sheet simulations and other things. Okay, and to a larger extent, we need to even optimize it. That's where the cost will also come in picture. Okay, so flow sheet simulation and optimization is another area that I'm going to talk about now. And of course, once the plant is designed, we need to operate it. So you need to have a control, or rather the dynamic behavior of the plant also needs to be predicted. So we need to have the proper control strategy to be designed for each piece of equipment at equipment level, at the same time on plant level, so that we get consistent quality in a continuous plant. Okay, batch plants control is not so important, because sometimes that control is provided by the labor itself. Like the labor or manpower who is working on the plant, they have a fair idea what to do and all that. So it is not automated to that extent. Okay, whereas continuous big plants, you really need automation. The entire plant is run by not more than 10 people per shift. Okay, and it is not easy to really manually do everything there, right? So that's where again a model will be useful. Okay, what should be the control strategy, which is the parameter that is more sensitive? If my composition goes up, I need to bring it at a particular level. What parameter should I change? There are 10 possible parameters I can change, but which is more sensitive and which will bring my composition down very fast? Okay, so all these predictions can be done, okay, with the help of modeling and simulation. Okay, is that the right answer, or
yes, sir. Thank you, sir.
yeah, okay, fine. In fact, it will be more clear now with this. Okay, now we have left behind three levels: molecular level, particle level, and reactor level. Now I am coming to flow sheet level. We have about 20-25 minutes, I think, and I will try and we have about 10 plus 15, yeah, 25 minutes. Yes. So I will try and cover that one case study and few examples in this. And many of you must have actually heard about this simulators, Aspen, HYSYS, ChemCAD, Pro2, and so on. What are these simulators? These are for flow sheets. Okay, these are for steady state and unsteady state simulations that one can do for the entire flow sheet. So if you go back to my first or second slide in which I had shown the flow sheet, we are now looking at the level of flow sheet. So far we were looking at the level of equipment, catalyst, particle size, particle mass transfer, and other things. Now we are going to the flow sheet level. The simulators, what can they do? Okay, they can perform simulation at operation level. That means that reactor and distillation column or other unit operations like mixers, heat exchangers, and so on. They can do simulation of the network of these operations, that is the entire process flow diagram. They can do simulation. They can do optimization. That means come up with the right flow sheet so that your cost is minimized. Okay, not just cost, sometimes you may have some different objective. Okay, and of course they can do dynamics. That's what I told you. Like you may have a control system so that you can operate the plant with a consistent product quality, right? So this is what commercial simulators are used for. And as teachers, we should not just use these simulators, but we should understand how they work. Okay, like what are the equations involved behind actually solving this. So I really urge you, it's not possible for me to really cover everything in this, but and probably some of it will be covered eventually. In fact, the next lecture is on reactive distillation by Professor Yogesh. So he would probably cover some of the equations dealing with reaction and distillation and so on. So we need to understand that. So don't just become an Aspen operator. Okay, like you should know what it is doing behind the curtain, behind the screen. Okay, what equations are being solved and all that. Okay, so it is very important that we understand the equations. If I had time, actually I would have spent some time to derive those equations for, say, a distillation column, and do degrees of freedom analysis, how many unknowns, how many independent equations you have, how much what is the input that you're going to give. So all this can be done. Okay, but in the interest of time, I'll just give you an overview with some case study. Okay, so let me just go to, so this is a flow sheet level. Okay, that's what I was going to talk about. This is a typical Aspen flow sheet that you will see. Those who have operated Aspen must be familiar with this. Is a mixer, this is a reactor, and this is a distillation column. Now Aspen would have individual models for this. Okay, simulators for this. Okay, and then at a flow sheet level also it will combine these simulators either in sequential mode or in parallel mode to solve the equations and predict the flow rate and every state variable, temperature, pressure, composition for every stream in this particular flow sheet. This is a very simple flow sheet that I've shown you. It can be as complex as what is going to come later. I will tell you, I'll show you rather. Okay, right? So equipment level, what can it do? So just an example of a distillation column. I want to do simulation and not design. Design is something that you have done, like McCabe method or Ponson-Sauerert method and so on. That is a design method and relatively simple in terms of calculation. I can do manual calculation on paper. But when it is a multi-component distillation, it becomes even more difficult. Okay, right? So now, earlier, like when we were students, like we didn't have simulators. Okay, that time 1985, 98, and all that. Now the simulators have come, and they are. If you have not incorporated in your curriculum, you should do that. Okay, it's high time. Every student should know what simulators are because they're used day in day out in industry. Okay, and that is one of the things that that industry would look at. Okay, like while selecting the candidates. Okay, so this is very important that every chemical engineering college and department should have simulator exposure to students. Okay, especially the process simulators. CFD and catalyst level molecular simulation are mostly advanced and still at its preliminary stage, and they are more important for research. But here, this is something that is used day in day out, okay, in chemical industry today. So they're very close to the actual commercial applications, right? Which is happening in manufacturing, right? So a particular stage, okay, sorry, this is a very vague picture, but basically at every stage I have the streams coming in, going out. I have different state variables. So all these are state variables. I'm sure you're not able to read it, X, Y, temperature, pressure, and so on. It's okay, no worries if you're not able to read it. Just try and capture the essence of it. So basically what am I doing is, like, this is one stage for which I am writing as so many variables, okay. I'll write mass balance, I'll write equilibrium equation, I'll write energy balance, I'll write if there is some source or sink term there, that will also have some equations associated with it. Then you will have summation equations for mole fractions. So this is called the MESH, mesh equations, okay, and they are written for every stage. And all the stages, suppose you have some n stages, you will have some 10-15 equation for one stage. So for suppose you have 50 stages, then 50 into what, 10, so 500 equations are to be solved simultaneously along with condenser and reboiler together, coupled, okay. It is not stage by stage calculation like what we do in design problem. So now we have to solve this simultaneously and simulate a distillation column. So coming back to my earlier diagram, when I say equipment level, I'm talking about this distillation column here, equipment level modeling that I'm doing here, okay, right? So now again, there are many models available, okay, for distillation column. You may have equilibrium model, you may have non-equilibrium model. So equilibrium model, depending on what assumptions I take, okay. Equilibrium model means the streams leaving a stage, they are in phase equilibrium, okay. That means I'm providing sufficient residence time and there is no efficiency like Murphy efficiency or something associated with the plate, okay. And mesh equations, I write down, I told you, M is for material, E for equilibrium, S for summation, H for energy. Okay, so these are the equations along with other supporting equations we need to write and solve them together. Okay, and all non-idealities and everything can be considered in the equilibrium model. So this is a very general model, and once we take help of some robust simulator or computational solver, we can relax many assumptions. Okay, and that's the beauty of simulator, right? So 500, 600 equations solving together is not a big deal. So I spend those who are operated, it doesn't really take much time compared to CFD. Like those who have done both CFD and Aspen, they must have realized CFD I need to wait because there I am making million cells, okay, and every cell is being calculated. Here you have 500 cells for which you are doing calculations. Of course, the equations are non-linear, and you may face some problems, which I'll come to that soon. Okay, non-equilibrium stage means like you have to consider mass transfer and heat transfer on every stage. The number of equations will increase and so on. Okay, and probably Yogesh will talk more about it in his talk. Okay, but if it is not covered in this, I would suggest some book. There is a nice book by Cedar on separation process principles, okay, in which he's given all the different types of models, equations, and so on. Okay, now I'm just making it more complicated. Like for example, there's a reaction that is taking place in a distillation column. Okay, then it is called as reactive distillation. Okay, and this is something that I worked on for quite some time in the past. Okay, so just to give an example, A plus B giving C plus D is a reversible reaction. Your Le-Chatelier's principle says that one of the products, if you remove during the course of the reaction, then the reaction will shift in forward direction. So you have a law of mass action explaining all these things. Is that clear? I think this is a 12th standard physical chemistry, right? The Le-Chatelier's principle. I'm not applying it. I'm doing engineering of that in reactive distillation. So this is what it is. You have a reactor, A plus B going in. You attach a distillation column to the reactor. You remove C in pure form. Let's assume C is more volatile. At least the volatilities are right. Right means C is more volatile, and D is the least volatile. I attach another column. So what is happening? So you have these three pieces of equipment together, giving you the product C and D from A and B. See, you don't need anything else in the plant. So in fact, we can combine these three units in a single unit, okay, which is called as a reactive distillation unit, right? if I give a feed of A and B to the reactive distillation unit, if I put the catalyst here where the reaction is taking place, I get C in pure form, I get D in pure form, right? So you can imagine you don't need anything else in the plant, just one column, okay? And that is actually done, okay? The methyl acetate process by Eastman Kodak, MTB process by UP, okay? All these are using reactive distillation on large scale, okay? And that you're so much saving in energy, so much saving in capital, and so on, okay? That's the advantage. Anyway, again, this is application point of view. Coming back to the theme of this particular workshop, that is computational techniques, modeling, and simulation, right? So now that we are combining reaction and distillation together, okay, you have more complexity coming in. Your equations that we are writing here earlier, they will slightly change. You will have source term of reaction, and reaction is always non-linear in nature, and because of that, non-linear means what? R is equal to CA square into CB, something like that. Square आता है या CA and CB का multiplication आता है, so it becomes non-linear, okay? So whenever non-linearity comes in, you have complications, and one of those complications I am going to talk about it in future, in a couple of slides, okay? Is this clear? Okay. So one example again from my lab, where we performed experiment in for butyl acetate synthesis from acetic acid and butanol. This is a laboratory setup. See, why we need to do experiments is to validate the model. Okay, because nobody will believe in model results unless they have a very good modeling, sorry, experimental support. Okay, so that's why you have this. Okay. So you can see the model predictions and the experimental data. There is not much disagreement. There is some disagreement, but I think it is reasonable considering that we are not tuned any parameter. Okay, so the model is able to predict the behavior of the distillation column, not just distillation, reactive distillation column. Okay, and solving all those equations simultaneously, M, E, S, H, and of course the reaction. Okay, right. They are what are they? They are algebraic equations, non-linear algebraic equations. Typically, a Newton's method can be useful, numerical analysis. Like, okay, but then again, you have to play with the Newton's method in cleverly, such that you have an algorithm such that you get the results very fast and ensure that you get convergence. See, the problem is convergence. Whenever you have non-linearity, no, convergence is an issue because it depends on the guess most of the times, right? If your guess is not right, then what will happen? You will not get a solution. Probably it will diverge or oscillate around the solution. Okay, but in this case, we are using simulators which are actually robust in terms of their computer and in terms of ensuring the convergence. So it is quite rare that sometimes the simulator comes out saying that no, convergence is not obtained unless your input given to it is not correct. Okay, that means sometimes no, you make mistake in giving the inputs, then the simulator can't really do wonders. Okay, for example, if you're A and B going in and I forget to give B, how can the product form? Like it's not a fault of simulator, it's a fault of person who's operating the simulator. Then it's like garbage in, garbage out. Okay, so it's that you need to know how the simulators operate, what equations are solved, and all that. Okay, it looks quite good here on paper, but we had to do a lot of study understanding how simulator works. Okay. So this is again a very just to look at this slide. Of course, I'm going to explain, spend some 5 minutes on this, but it is important. What happens actually because of non-linearity and the role of again the computational techniques coming in picture here. Okay, now, what's the title of this slide? Non-linear dynamic effects. What does it mean? It means that because of the non-linearity in the equations, where is the non-linearity coming in? Y is equal to mx plus c is a linear equation if you consider y as output and x as input. Okay, but at the same time we say y is equal to mx square plus c, it is non-linear equation, right? Similarly, suppose you have two equations, so y is equal to mx square plus c, p is you have two variables, y is equal to mx1 square plus n x2. Okay, and y2 is equal to again some function of x1 and x2, right? And they are non-linear. Okay, somewhere square is appearing. Sometimes it may appear in the form of multiplication of x1 and x2. It may appear in the form of division of x1 and x2. It may appear in the form of e raised to x. So all this is non-linearity, right? And where does the non-linearity comes in our model? Enthalpy is for non-linear function of mole fraction. Okay, reaction rate is non-linear function of mole fraction. So all this non-linearity, vapor liquid equilibrium is non-linear. Y is a function of x, which is non-linear, right? Simple alpha x divided by 1 plus alpha minus 1x. Okay, it's a non-linear equation. Okay, so this, because of this non-linearity, like you have issues in your operation, modeling, simulation as well. And I'm going to explain this to you. Okay, what are these? So this is, look at this, multiple steady states. Okay, those who have again taught reaction engineering course, I think Fogler's 7th or 8th chapter on heat effects, CSTR gives multiplicity, multiple solution, right? Why this multiplicity is there? Because mathematically, if you look at the model, it is non-linear in nature. So what does it mean? For a particular reboiler duty, okay, it is possible that I may get this conversion or this conversion or this conversion. There are 3 possible conversions under otherwise similar conditions. So you are not changing anything, but you are likely to get 3 different results. What does it depend on? It depends on how you operate your column, how you start your column. So dynamics is also important. Okay, so most of the times, we just concentrate on the steady state behavior. We write algebraic equations, and by writing algebraic equations, you are going to get this thing. Okay, that there are 3 possible solutions. Now, what is the physical significance of that? The physical significance is that one solution will be obtained if I start the column this way. The other solution will be obtained if I start the column in some different way, right? So how you start your column also matters. Okay, sometimes, not always. And when does it happen? When your model is non-linear in nature, but always, again, even if it is non-linear, sometimes you may not get multiplicity. In very peculiar cases, you may get multiplicity, and that can be captured very well through simulations. See, imagine its significance. If you don't know that this column is likely to get multiplicity, imagine you are operating a column. Okay, you are getting some purity. Nice, you are happy, 98% purity at the top. Okay, it is operating smoothly. Now, all of a sudden, few seconds, okay, only few seconds, which may go unnoticed also. Operator may not see that also. That your input composition changes. Likely to change ना. अरे पंप वगैरह चलता है तो कभी कभी पंप थोड़ी देर के लिए कम फ्लो रेट से फ्लूइड भेजेगा. Okay, so because of that, like one particular composition may change if you're mixing later and all that. So this change, which is happening only for a few seconds or minutes, okay, can take you from the earlier steady state of 98% purity down to 20% purity, okay, 60% purity. Okay, that is possible because now column has switched over from one steady state to other steady state. Now, if you come after 5 minutes and an operator saying that, okay, everything is same, but why am I not getting purity? Everything is same. It has happened because when you are away from the control room, like within 5 minutes, there was a fluctuation and that has resulted into this particular behavior. It's like a magic, no? So, but it is possible in some cases when you have non-linear effects. Non-linear, that is what it's called as non-linear dynamics. And if you had done modeling before, and you would have known that, okay, this system is likely to give multiple steady states, then I can define a control strategy in such a way that I always remain at a higher steady state of purity or conversion or whatever. Okay, this is a reactive distillation column, so conversion is one of the performance parameters. This is another behavior. This is again, you see, if you have equilibrium stage model, TAM, tertiary amyl methyl ether. Okay, with respect to time, if you are sitting at bottom and looking at the purity, it is continuously oscillating. It is oscillating, but it is sustained oscillation. Okay, sometimes it may not be harmful, okay, because average that you are going to get is okay. But you start wondering why oscillations are coming. Everything is my input parameters are not changing, but still it is oscillating. This is again another non-linear dynamic effect. If you want to avoid that, again you can have some control strategy to break these oscillations. So what I'm trying to say, of course, I'm going slightly at an advanced level, but yes, it is important to know this because on a large scale, you may have some unusual, unknown effects that may come into picture unless you have done modeling, simulation, and computations to identify it for a particular reaction or distillation system. Okay, right? Any questions before we go ahead?
Sir, there is one question in chat box.
Okay, fine.
Question is like, how different is to model a microreactor compared to a conventional reactor?
Oh, good question. I need to tell you about a theory of microreactors. We have about 3 to 4 minutes left. I'll try to finish that in that, but there is another case study I wanted to cover. If you are giving me 5 minutes more, I will try and cover that. Is that fine?
Okay, sir. You can.
So instead of 12:15, we'll finish at 12:20.
Yes, sir. Okay. Okay. Sir.
All right. Okay. So micro reactors. Okay, it's another field altogether. Why they are important? Okay. First of all, they are important because of lower dimensions. We get so many advantages. One advantage is like you get very high surface area to volume ratio. And if the reactions are highly exothermic, sometimes purposely you make them slow so that the heat effects are less significant. Okay, but if you go to micro reactors, you are able to remove the heat very well so that you can get a reaction going at a higher rate. You can afford to get the reaction going at a higher rate. Okay, that is micro reactor. Second advantage of micro reactor is that you can get some nice mixing at molecular level also. Okay, because of lower dimensions. Third advantage of microreactor is that you may get in multiphase reactions, may get higher interfacial area per unit volume. Okay, you have different regimes in the reactor. Okay, so you will have, suppose, gas liquid reaction taking place, your interfacial area per unit volume is more there. Okay, so again you'll get higher mass transfer rate and the overall rate may go up if the reaction is controlled otherwise by microreactor in a normal conventional reactor. So these are the advantages of microreactor. Now coming back to your question of how modeling will differ, modeling will not differ. These values, okay, your interfacial area which was already there in your model, these values will change. The model will remain same for the reactor. Okay, right? Flow patterns may change. Then again you have to look at the E curve and other things and try and understand. Okay, if you want to really capture the flow patterns also. Okay, but most of the times in micro reactors, since the diameter is smaller, the flow pattern is well defined, is laminar flow, so you get a parabolic profile. Okay, you don't need to worry much about whether there's a back mixing happening and all that. Okay, right? So coming back to your question, the situation scenario may change, the equations will remain same, the model will remain same, but we need to aware of certain effects that may be prominent in micro reactors. Okay, and we cannot ignore those effects and cannot make assumptions on that and go ahead. So while writing the model for micro reactor, it's important that we should not ignore this, for example, this heat effects or interfacial area enhancement. Okay, so these are the effects which are going to show the potential of microreactor, the advantage of microreactor, and if we make some silly assumption there, then you may not be able to capture that effect which is already there. Okay, so that is how microreactor are different from the normal reactor. But in terms of the concepts, in terms of the science and physics behind it, it is not different. Okay, did I answer your question?
Yes, sir.
Yeah. Okay. So now, sorry. Shall we go ahead?
Thank you, sir. Thank you.
Yes, sir. Yeah. So I had some 5-6 slides after this. Okay. I am going to go very fast here because we are running out of time. Just to let you know that this project was undertaken for an Australian company, and we have a Monash Academy in IIT Bombay. So I'm just acknowledging all the people who are involved in this project. Okay. So flow sheet level, and I mentioned one advantage, one more purpose of flow sheet simulation is optimization. Okay, so that is very important. So at flow sheet level, if you do optimization, then you are able to save a lot. Okay, so that's where the role of modeling simulation will come at flow sheet level as well. Okay, so that means Aspen is able to kind of simulate the entire flow sheet, but how do you know that the results are good? How do you know that the results are optimum? So here is a case study where we actually worked on it and tried to somehow tackle this complex problem. In fact, one entire PhD has gone in this. Okay, so now we are looking at coal to ammonia. Again, the application is that you have a gasification plant and you're trying to gasify coal, making CO plus H2, that is syngas. You will do syngas conditioning, then water gas shift reaction to adjust the CO and hydrogen ratio, and then you are removing CO2 and H2S from the gas mixture so that only hydrogen goes to the ammonia reactor. And those who are teaching process chemistry or process technologies to undergraduates are well aware of this process, except that sometimes you have primary reformer, secondary reformer when you are using natural gas or naphtha. Okay, and of course here you are using coal as your raw material, so you are doing gasification for which pure oxygen is required, and you need air separation unit, and the nitrogen separated from air is going to the ammonia plant. Now, what is the problem here? Optimization of CO2 capture process in context of its use. So now I don't have just one particular optimization. Typically, when you say optimization, I need to optimize the cost. Okay, so I need to reduce the cost. Everyone says like ultimately it's money that matters. Okay, so you have to reduce your cost so that you get the best performance. Okay, but here we have another optimization function, that is environment. So people have started looking at environment also. Sometimes you may achieve the things at less cost, but you are damaging environment, then there's a problem. So you have two objective functions here, that you reduce the cost, at the same time you subject environment to less pollution. Okay, minimum pollution, right? This is the process. Of course, what I'm going to give you the example of this part where I am capturing CO2 in absorption. Okay, and that is elaborated here. You are capturing in absorber. Methanol is used, a Rectol process. I don't know whether you heard about it. Under cryogenic conditions, methanol is used to absorb CO2, then solvent washing, CO2 compression, and for 100% CO2 is separated. Okay, and this is of course the entire process. I've just, this dotted part is the one that we are actually concentrating on. Okay, so typically for optimization, you have to minimize or maximize the function fxy, where x and y are decision variables, and with given constraint on x and y. Okay, so this is the optimization problem. In most of the cases, f is the cost which is to be minimized. Okay, example is like you have, say, reflux ratio in a distillation column. So in order to minimize the cost, you have optimum reflux ratio, which is normally 1.2 to 1.5 times the minimum reflux ratio. Okay, so those who have not exposed to optimization, I thought I'll just cover some basics of optimization here. Now coming back to your ammonia process, okay, you have two objective functions. Okay, F1 and F2. What is F1? F1 is minimization of cost, and F2 is minimization of CO2 release to the environment. Okay, so carbon dioxide capture. Okay, so that is what we are trying to do. So multiple optimization. Okay, so but they are conflicting in the sense that you have a production cost and you have CO2 footprint. Okay, that means if you want to increase reduce the CO2 footprint, your production cost will go up. Okay, and that's where the problem is, right? So this is something called the Pareto curve. Okay, and any point on this? Okay, so if I say that I want to do product, I want to have production cost only this much. In that case, the minimum CO2 footprint will be this. All the other points are here, so but the minimum will be this. You can't reduce your CO2 footprint below that. If you want to reduce your CO2 footprint below that, then you have to increase your production cost. And that is as simple as that. It's a logic, right? That I am capturing CO2. If I'm not letting it go to atmosphere, that means I have to put in more money, right? And that is what it is. So this is a Pareto curve, okay? And we have to actually travel on this curve. And final objective is to get this curve, okay? And that is what we obtain, okay? So this is a problem definition. The two objective functions, the cost for ammonia production cost of ammonia, and carbon footprint. Okay, so one has to be minimized, and carbon footprint also has to be minimized, but they are conflicting each other. Okay, they are conflicting each other. And what are the decision variables in the plant? So we have identified this decision variable: oxygen flow rate to the gasifier, then steam to the temperature shift reaction, the first stage flash temperature, fourth stage flash temperature for carbon dioxide absorption, chill methanol to the absorber, temperature change. These are the state variables, or these are the decision variables like X, Y I mentioned. There were 2 there. Now we have 3 plus 3 plus 2, that is 8 variables here. Okay, right? And what is a constraint? The constraint is that you should sorry, your amount of NH3 produced should be 12,050 kilomoles per hour. That production capacity is given to you. So that is a constraint on your optimization problem. Okay. Sorry, it is not moving forward. Yeah. This is your Ectisol process, your absorption of methanol, and then flashing to get rid of CO2, and then another regenerator wherein H2S and CO2 are removed. Okay, this is a process flow sheet. Okay, let's not try and understand too much about it. What I'm trying to tell you is how we solve this problem. The possible solution is this: detailed modeling can be done, but there are many variables. Now you need to do optimization. The simulation itself becomes a constraint for you. Okay, that you have to keep changing these values of decision variables such that you minimize the cost and minimize the carbon footprint. So what we have come up is a surrogate model. Okay, so a simplified model. So every time when I do my iterations, I don't need to actually solve this simulator. Okay, so based on the simulations independently, we came up with a surrogate model. Now what is surrogate model? In simple terms, it's a correlation. Okay, so like you have come across Siderted correlation, Dittus-Water correlations. Okay, what do? I do experiment and feed that data in some form of correlation. Instead of experiments, I have done simulations independently in Aspen. Okay, and have come up with a correlation. So these are all correlations for independent output that we have, and in the bracket your decision variables. Okay, so that way my computational load goes down drastically. So we have used this technique or trick of using a surrogate model for Ectisol process. These are the inputs and these are the outputs, and every output is expressed in terms of input in the form of correlation like this. Okay, and that's why like our computational efforts have gone down, and we are able to get the same effect of what we would otherwise get by the detailed model. Okay, and with that we've used NSGA, that is non-sorting genetic algorithm, okay, to do this optimization simulations. So what we do, you have Excel platform. In Excel you have objective function defined, decision variables defined, constraints defined, and other NSGA2 parameters. That means how many values of decision variables that I need to check, and all are specified here. So decision variables come out, you do Aspen simulation with the help of surrogate model inbuilt in Aspen. Then there is a separate refrigeration unit that we modify, that we optimize separately, and then the objective function values will go to Excel, and these objective function values are given to another optimizer, wherein which is based on genetic algorithm. Now genetic algorithm is something I wanted to spend some time here, but again we don't have much time. But what is genetic algorithm is like in a decision variable space, you actually come up with some random values of decision variables, and based on the objective function values, you change those values, okay, in such a way that it evolves, okay, and there is a separate strategy for that. So it genetically evolves based on what results you got. And suppose I'm generating 50 values now for decision variables here, they will get modified based on this algorithm, which is taking the help of objective functions and constraint, and will generate new decision variables that will go to this, and this will go on happening, and finally you will get a Pareto curve like this, okay. And what we have given in this is the comparison between business as usual, that means without surrogate model, and the other one is a surrogate model. And surrogate model achieves the values very fast, okay. So within 250 actual model evaluations itself, we got the surrogate model giving the Pareto curve, whereas the business as usual, that means this dark black this thing circles, okay, they could converge to the surrogate model only after 750 evaluations. So we have reduced the computational time significantly and achieved the results faster, okay. This is about the decision variables. So that we found that there are two decision variables, like the pressure and the purge. Oh, sorry, pressure and purge, okay, they are actually the most sensitive, and other ones are always hitting the bounds given to them, okay. So pressure in the first flash, pressure in the last flash, and the purge, okay. If this is straight line like this, okay, that means it is the constraint that is hit, okay, whereas there is a scope for changing these values to get the Pareto curve as per our requirement, okay. Sorry, I went very fast here. What you should take home from last part of this this presentation is that there is optimization possible at flow sheet level, okay, with genetic algorithm and all, which are available in open source. We don't need to buy these softwares, and but of course it is computationally very expensive exercise, like something that we do on molecular level, okay. But there are possibilities that we can simplify it by using surrogate model, okay. Surrogate model is like a correlation, and instead of experimental data, we are using first principle simulation data to come up with a surrogate model, okay. Sorry, even if that much you have captured, I think that's good enough. And if you want to know more about it, I can pass on some literature for further reading. With that, let me thank all of you. Sorry, I have gone a bit more than what was given to me, the timing, and I thank again the organizers for Dr. Patil, the principal sir, for inviting me to give this talk. I hope I was able to meet your expectations. Any further questions, I will be very happy to attend them. Thank you very much for your attention.
Thank you, sir. So any participant who have questions, they can ask. So I think there is no more question. So now I request Professor S.Y. Pawar sir to deliver a vote of thanks.
Hello, good afternoon one and all. Myself Sanjay Pawar, on behalf of Organization Committee and Department of Chemical Engineering PVPIT, I would like to express our sincere thanks to Dr. Sanjay Mahajani sir for an excellent coverage to process modeling, simulation, and computational complexities in a chemical process. He has shown an important informative picture regarding the size and time scale of the entire life and any industry like this. So as of we know that the accuracy of the reactor design depends upon kinetics, residence time distribution, mixing behavior of the fluid, and the degree of segregation. And in addition to this, mass transfer and heat transfer effects. He has highlighted about the modeling of different types of reactors and reactor combinations, then scale-up issues and related problems. So next thing, he has explained very well about the computational fluid dynamics. In that, he has considered the case of underground coal gasification. He has focused on the modeling of reactor with the help of E-curve. He has also given idea about the different modeling approaches of a chemical process. In that, he has given example of modeling of a distillation column, in that equilibrium model and non-equilibrium model. He also explained very well about the how CFD is helpful at a pilot plant level, and concept of the flow sheet simulation, optimization, and commercial plant. Then about model verification and validation through the experimental work. At the end of session, he also introduced the concept of modeling of microreactors. Here, we will experience the low number of scale-up issues as we go to the, instead of scale up, we go scale down. He had given very good explanation to each queries and questions of the participants. At the end, I express my thanks, sincere thanks to the sir. Thank you, sir.
Thank you. My pleasure. Thank you. Shall I leave the meeting?
Thank you, sir.
Thank you.
Yes, sir.
Yes, thank you.
Thank you. Bye.
So we'll stop our first session here, and we'll start our second session at 1 p.m. sharp. So please join at 1 p.m.